Welcome back. If you look at the perspective of bulk volume production of PV modules, these figures would suggest that the thin film PV technology becomes less competitive on the markets in reference to the crystalline silicon PV technology. This might be true for bulk volume production of PV panels, as for such type of production and market, the metrics of both cost price per watt peak and the module efficiency to achieve low cost prices of the non-modular cost would be the only important metrics. However, more metrics play an important role in the integration of PV depending on its application. Therefore, many different PV technologies facilitate various different markets and applications which might be growing as well in the future. The objective of this last video is to discuss these metrics and the relation between these metrics and the various PV technologies. Important metrics are, for instance, the weight of the modules. Not every roof or construction can carry the weight of glass encapsulated modules. This means lightweight modules are required. Neither can every PV module be easily integrated on curved surfaces. So flexibility of module might be a crucial design parameter in some applications. In other applications, you would like to cover the entire available surface, which is not possible if you have only 1.5 square meters of rectangle-shaped panels available. So a customized shape of modules would be helpful to achieve this. As discussed before, the materials to manufacture the module should be cheap and abundantly available as well. In other applications, the amount of energy per surface is important. So then the only efficiency would be the leading metric. For some applications, the aesthetics of the modules play a more dominant role. Color, prints, and the appearance of modules might be a more important metric than efficiency and cost price. Another design metric is the shading tolerance of PV modules, which starts to play a role in the PV application into building elements. The metrics can also be climate related. The effect of temperature dependence on the performance of the modules might be varying from climate to climate. So many different metrics are related to many different types of markets. You might call these markets a niche market, but every 1% of the current PV market would represent over 1 gigawatt peak of business. I would like to finish the part 2 of this solar energy MOOC on PV technologies with reviewing some metrics of the various PV technologies and show some interesting new applications. First, we review the crystalline silicon PV technology. The big advantage is the relatively high efficiencies for the modules and the low cost price per watt peak, what has been achieved by the enormous upscaling of the production capacity in Asia. Another important aspect of the crystalline silicon is the reliability. Silicon PV material is very resistant against water and humidity. Even in very old, poorly encapsulated crystalline silicon modules, the heart of the PV device keeps on working. The anti-reflection coating might have been peeled off, but as long as the metal contacts do not peel off, the PN junction keeps on operating under light exposure. Many PV technologies are based on PV materials or supporting layers like TCOs that are not resistant against water. A disadvantage of crystalline silicon modules can be that they lack the flexibility to adapt to the building geometry, its lower performance under shading, and the modules are sensitive to mechanical stress. Bending or walking over the modules might result in breaking off the wafers. The 3.5 PV technology results in the highest efficiencies for devices and small-sized modules. If the power per area is the most important metric for PV integration, 3.5 PV technology is the logical choice. In case of space applications like satellites, the metric power per area and power per mass is the most important one. 3.5 PV modules can be highly efficient, lightweight, and flexible. For concentration photovoltaics, high efficiency per small area is the most important design metric. Therefore, 3.5 PV technology is the most suitable technology for that application. The challenge for the 3.5 PV technology is the cost price per watt peak due to expensive processing technologies and resource materials. Alta Devices has been the pioneering company that tries to tackle this disadvantage by new innovative processing technologies for the thin film single junction gallium arsenide solar cells. The biggest disadvantage of thin film silicon is the relatively low efficiencies for the PV modules, making the non-module cost of the PV system more expensive than competing technologies like CIGS and cadmium telluride. However, for lightweight, flexible modules, thin film silicon is the cost-effective solution. As silicon is resistant against humidity, the requirements of the water barrier in the encapsulated material is much lower. This allows much cheaper encapsulation approaches, which is usually the component that determines the cost price of flexible modules. This allows high-tech integration of modules in building elements like in this picture. This technology allows easily customized module shapes and high aesthetical applications. In addition, the multi-junction modules have a lower temperature dependence, which makes the performance less sensitive to temperature. An important advantage of the CIGS PV technology in reference to thin film silicon PV technology is that it has a higher efficiency for the PV modules. This makes CIGS PV technology more competitive in the configuration of glass encapsulated modules, like the example here from Solar Frontiers. An advantage of the CIGS PV modules is that it can be integrated in flexible modules as well. However, the requirements for the encapsulation material are higher for this technology. The advantage of the cadmium telluride PV technology is the relatively low cost price in combination with the fastest learning rates for the cadmium telluride PV modules. Therefore, cadmium telluride is still competitive with the multicrystalline and monocrystalline PV technologies. Another advantage of all thin film PV technologies like cadmium telluride is that due to the typical monolithic interconnection schemes of the individual cells, the modules are less sensitive to shading effects. If the edge of the shade is perpendicular to the length direction of the individual cells, the output power scales roughly linearly with the fraction of the module area that is not shaded. Wafer-based modules have a step-like relation with the illuminated fraction of the panels. For organic PV technology, several different types of modules have been demonstrated. Here you see a highly aesthetical module design from VTT Technical Research Center in Finland. The advantage of the organic PV technology is that it allows to make semi-transparent PV devices and can be processed in complex shapes on geometrical challenging surfaces. However, the challenges for OPV technology are its low module efficiency and instability of the module performance over its lifetime. The perovskite PV technology has similar advantages like the OPV in terms of semi-transparency up to implementation in flexible products. In contrast to OPV, higher conversion efficiencies in the range of 25% have been demonstrated for perovskite PV devices with sizes below 1 square centimeters. However, the high efficiencies for module sizes have not been demonstrated yet, as discussed earlier. The big challenge for perovskite solar cell is the instability of the material. This needs to be tackled first before perovskite PV technology can be successfully scaled up on industrial level or be integrated into a tandem cell architecture with a crystalline silicon PV cell as the bottom cell. Summarized, every PV technology has its specific pros and cons. The choice for a PV technology for a specific PV application depends on the special conditions, requirements, and challenges of the photovoltaic application. I hope that you have enjoyed the second part of this solar energy MOOC on PV technologies and that you gained knowledge and insights of the wide diversity of existing PV technologies. This knowledge will help you in the future to make the correct design decisions for new innovative PV technologies and PV systems. Here you see several new applications going from integration of PV technology in special facades, printed modules mimicking the bricks in a wall, up to bifacial modules. You now have the knowledge to help in designing such types of innovative products. But what is the impact of the position of the sun and solar irradiance on the PV module performance in a real outdoor situation? The PV module is only one single component in a PV system. What are the technical specifications and the operation principles of the other components like inverter, DC-DC converters, batteries, charge controllers and cables? How to design a PV system ranging from a residential rooftop system to a large-scale utility solar farm? What are the economics and the business models of solar electricity? And how does the ecology of a PV system look like? All these topics will be addressed in the last part of the Solar Energy MOOC on PV systems. For now, I wish you good luck with finalizing the last exercises, and I hope to see you back in part 3 of the Solar Energy MOOC on PV system. See you in the next course.